lecture series on complex analysis for undergraduate students. Today's lecture is on residue integration method. Till now we had learned many integration methods, or in many way we had find out how to solve the integrals for the complex functions. In all those methods we had learned that is the function has to be analytic in the region of integration. We had also done the Cauchy integral formula, where we had find out if the function is not analytic at complete domain, but it fails to be analytic at one particular point. We have taken that point out and we had used the disk where the function was analytic, and on that boundary we had find out that function is analytic, and there we had used one Cauchy formula. Today we will learn some more integration methods for functions which are not analytic at certain points. Then what will happen? We had learned in last lecture, when the functions are not analytic at some points, those points we have called singular points. We had classified the singular points as poles and essential singularities. Now we would have one more classification of isolated singular point, that is removable singular point. When all bn's in the principal part of f at isolated singular point z naught are 0, the point z naught is called a removable singularity. In other words, the definition of the removable singular point could be, why we are calling it removable, because it can be removed. What it is saying is, a function f has a removable singularity at z naught if f is not analytic at z naught, but can be made analytic by assigning a suitable value of f there. What does it mean? It simply says is, the first definition says is that in the principal part all the bn's are 0. What it says is that that singular point may be because the function is not defined at that point. So, we would call it removable singularity, because if I could define a suitable value of the function at that point, we could make the function analytic. See for example, what we are talking about here. Let us take this function e to the power z minus 1 upon z. As such, it is looking is that the numerator is our analytic function. Denominator, of course, when z is equal to 0, I would not get it as analytic, but see what is happening at z is equal to 0. Does this function is defined at z is equal to 0? When z is 0, e to the power z would be 1. So, 1 minus 1 is 0 and the denominator is also 0, that is the function is not defined at 0. Let us see, if I write the Maclaurin's expansion for e to the power z, that is 1 plus z square upon factorial 2 and so on. So, 1 and minus 1 I would cancel it out and divide it by z, we would get 1 plus z upon factorial 2 plus z square upon factorial 3 and so on. You see, in this expansion, since at z is equal to 0, this function is not analytic, that is z is equal to 0 is an isolated singularity. So, of course, the Laurent series can be written, and if I am writing this Maclaurin series, I am finding out it is not having any principal part, that is none of the bn's are present over here. Now, this is the case which we are talking about, that z is equal to 0 is an isolated singularity which is removable. How it could be removed? You see, if what we are saying is that the function is not defined at z is equal to 0. If I take limit of this function as z approaches to 0, what I would get? I would get this constant 1 and all other points would be all other terms would become 0. So, now if I define the function, so the function is not defined at 0, that is why it is singular. So, if I define f0 as 1, then you will find out that now function is analytic. Now, you can check that this function fz e to the power z minus 1 upon z for all points z not equal to 0 and is equal to 1 for z is equal to 0 would see that is this is an analytic function. One more similar kind of example is sin z upon z. Again you find out that is z is equal to 0 is an isolated singular point for this function sin z upon z. But we see what is f at 0. If at 0, sin at 0 is 0. So, it is again 0 by 0, that is indefined form. Now, let us write again the Maclaurin's expansion for sin z. It is simply z plus z cube by factorial 3 plus z to the power 5 upon factorial 5 and so on. If I divide it by z, I would get 1 plus z square upon factorial 3 plus and so on. Now, again we find out as z approaches to 0, this limit of this f z would be 1. So, now what I would define? I would define f 0 as 1. So, now this function f z sin z upon z for z not equal to 0 and 1 for z is equal to 0, this is now analytic function. So, now let us move to one more result where we would relate the 0 and the poles for a function if the function can be written as the rational of two functions, poles and zeros. The result says is f z be analytic at z naught and has a 0 of order m at z naught, then 1 upon f z has a pole of order m at z naught, and the same is true for h z upon f of z if h z is analytic and z naught is not 0 of h z. So, what we are saying is we are relating the zeros of analytic function with the poles of the analytic function. We are saying is if f z is analytic and has a 0 at some point, then 1 upon f z will have pole at that point and the order of that pole would be same as the order of that 0 for f z. Now, this is simply for 1 upon f z. Now, if I do have that my function can be written as a rational in the rational form, that is it is a ratio of two analytic functions h z upon f z, where both h z and f z are analytic and f z has a 0 at z naught, but that z naught should not be the 0 of h. Then also that z naught would be the pole of this new function h z upon f z, and the order would be again the same for what is the order of 0. Let us see that is how we can show that this will happen. Just proof of this. Since f z is having a 0 at z naught of order m, that says is we could write f z as z minus z naught to the power m into z z, where z z is an analytic function and z at z naught is not 0. So, 1 upon f z if I do write, I could write it as 1 upon z minus z naught to the power m into 1 upon g z. Since g at z naught is not 0, so 1 upon g at z naught, that will also not be 0. So, write 1 upon z at z z as say p z. So, what I would write 1 upon f z I could write as p z upon z minus z naught to the power m, where this p at z naught is not 0. What it says is that I am having this new function 1 upon f z, which does has a principal part. In the principal part contains the in the denominator z minus z naught to the power m, and its numerator is p z, which is not 0 at z naught. What it says is that I am getting a principal part with m terms. So, z naught should be the pole of this new function and order of that pole must be m. So, since g z naught is not 0, so p z naught will also not be 0. So, 1 upon f z has a pole of order m at z is equal to z naught by definition. So, now if I do have here rather than p z, if I do have h z, so what I would have that p z would be now my h z upon g z, and at z is equal to z naught, neither g z is 0 nor h z is 0. So, p z would also not be 0 at z naught. What it says is that the function would remain defined, and so the theorem would be true for this h z upon f z also. Now, from here, because we are talking about all these isolated singularities, their kinds and the behavior of the function near them, now we want to move that integration method because of this behavior of this function near these isolated singularities. For that, let us first again come to this Lorentz series representation and this principal part. We do know that when Z naught is isolated singularity of f, then the function f can be represented by the Lorentz series as summation n is running from 0 to infinity a n z minus z naught to the power n plus n is running from 1 to infinity b n upon z minus z naught to the power n in the disk 0 is less than z minus z naught is less than r. And this a n, so this is the disk and this principal part of this is summation n is running from n to infinity b n upon z minus z naught to the power n, and from this principal part we have identified the isolated singularities. We had also learned in that when we have defined this one that b 1, that is especially for n is equal to 1, b 1 would be 1 upon 2 pi I f z t z, because b n's we had defined as 1 upon 2 pi I integral along this closed contour f z upon z minus z naught to the power minus n plus 1. So, when n is equal to 1 I would get the denominator will not be there, I would get simply f z. We had called this b 1 as the residue of f at isolated singular point z naught. So, now we are defining residue. Residue of any function f at isolated singular point z naught is been given by 1 upon 2 pi I integral along this curve C of f z d z. So, we are having is that f z has a isolated singular point at z naught, then we are defining this one. Now, rewrite this one integral, because here what we are having is in the right hand side we are involving an integral. Rewrite this one, what we could say integral f z d z on this closed contour C is 2 pi I times b 1. What is b 1? b 1 we called is the residue of f at this point. This another notation for this is we are writing that residue at z is equal to z naught of f z. So, 2 pi I b 1 or 2 pi I residue of f z at z is equal to z naught. Now, what we have got? We have actually got one integration formula. Till now the integration formula we had got is the Cauchy theorem said if we are having f as analytic in the whole domain, then integral along any closed contour would be 0 for analytic function if the function is analytic inside that closed contour and on that closed contour. We had Cauchy principle, we had Cauchy integral formula which said is that is if we do have z naught as an interior point of your C, we had got that is f of z naught we could define as integral along that closed contour f z t z with 1 upon 2 pi I. Now, there also f was analytic completely. Now, we are having is this reason, this closed contour C, the function is analytic on this contour and in its interior except at point z naught, because z naught is isolated singular point. This C I could take any circle such that it is a small neighborhood where it makes is that z naught is isolated singularity. So, z naught is isolated singularity of the function f. So, now f is not analytic. So, when f fails to be analytic or f has one singular point inside in the interior of this closed contour C, we could evaluate this integral as 2 pi I times residue of f at this one. If it is a singular point, we do know we could write it as Lorentz series or we could find out its residue, that is in the principal part the first the coefficient of 1 upon z minus z naught, that is we have called residue and that we are getting from here. Now, since we do know that Lorentz series we are not always obtaining by those integral formulas, we are obtaining the Lorentz series in many manners. That says is this residue can be obtained without really integrating it. Thus, it says is that this integral can be obtained using the Lorentz series and the residue at that isolated singular point. Let us see, that is what I am saying is how we are doing it with the help of some examples. If f is analytic in and on a simple closed contour, then integral along that contour f z dz would be 0. This we do know, this is what is our Cauchy integral theorem. Now, if I do have f is analytic in C except at z naught, then this just now the result which we had obtained, that set is integral along this contour of f z dz is 2 pi I times residue of f at z is equal to z naught. So, now we have got new formula, and as I said, this Lorentz series can be obtained by many methods other than the integration. This could help us in finding out the integration, or the evaluation of this formula would help us in evaluation of integral. Let us see one example. Evaluate this integral e to the power minus z upon z minus 1 whole square dz on the circle mod z is equal to 2, that is, it is a circle with the radius 2 and center origin. Let us see the circle with radius 2, center origin. Let us see this function e to the power minus z upon z minus 1 square. The function is a ratio of two functions. The numerator e to the power minus z, this is entire function. The denominator is z minus 1 whole square. This would have 0 at 1 and the order of the 0 would be 2. So, what we do have is this has a pole of order 2 at 1, or it is isolated singularity at 1. 1 is inside this region of integration or this contour. Now, I can apply my residue result. Using this e to the power minus z as this Maclaurin's expansion, I could write the Lorentz series expansion of f z as you see here, e to the power minus z upon z minus 1 whole square. Now, you see is that is how I am writing the Lorentz series. I am not writing this Lorentz series finding out the integration methods. E to the power minus z I could write as e to the power minus 1 into e to the power minus z minus 1 upon z minus 1 square. Now, e to the power minus 1 I will take common, and I would write the Maclaurin's expansion of e to the power minus z minus 1 using this one. So, what it would be, summation n is running from 0 to infinity z minus 1 to the power n upon factorial n. So, now if I take this one, what I would get? I would get e to the power minus 1 upon z minus 1 square minus 1 upon z minus 1 plus 1 upon factorial 2 minus z minus 1 upon factorial 3 plus z minus 1 whole square upon factorial 4 and so on. So, after that these terms from here the terms would be summation a naught summation a n z minus z naught to the power n, and a naught is 1 upon 2. This is the principal part, 1 upon z minus 1, 1 upon z minus 1 whole square. And so, we of course, as I said is from here this has a pole of order 2 at z is equal to 1. Now, what is the B 1, that residue? Residue is the coefficient of z minus z naught 1 upon z minus z naught. The coefficient of z minus 1 is here minus 1, and of course, this e to the power minus 1. So, minus e to the power minus 1. So, what we have got, this residue B 1 is minus e to the power minus 1. If I use this formula which says integral along this contour C f z d z is 2 pi I B 1. So, 2 pi I into minus e to the power minus 1 or minus 1 upon e. I have got the integral minus 2 pi I upon e. You see, that is because for this function we could write its expansion, Lorentz series expansion, or we could find out the principal parts, or we could find out the residue. So, we could use this integral, we could find out the integral where the function is not analytic at one point inside this one. Let us see one more example. Evaluate the integral along the contour C e to the power minus 1 upon z square dz. Again the contour is that circle with radius 2 and center 0. Let us see this function e to the power 1 upon z square. Now 1 upon z square is analytic in C with isolated singularity at origin. So e to the power 1 upon z square will also be analytic except at origin, and that origin would be actually isolated singularity. So again I would use my result of this residue one, and for that we would use the integral. So for that we have to find out, first we have to write out the Lorentz series expansion for e to the power 1 by z square, so that we could find out the residue at z is equal to 0. If I write e to the power 1 by z square, it would be actually 1 plus 1 upon z square plus 1 upon factorial to z to the power 4 and so on, and this expansion is valid for all z between 0 and infinity. From here if you see there, what is the residue? Residue should be 1 up the coefficient of 1 upon z, that is 0 here, because I do not have any term of 1 upon z. That says is this integral would be 0. So we have got that the function is ceased to be analytic at origin, which is inside this contour, simple closed contour, but is still the, for this function e to the power 1 by z square, the integral along this closed contour is 0. It is just because the residue at that point is 0. Here we cannot use this Cauchy integral theorem which says along any closed contour it would be 0, because then the function f has to be analytic throughout the region, but this function is having a singular point at origin. One more thing is, that is whenever we are trying to find out this integral, we have to be very cautious, that is find it out whether that singular point is inside the contour region or not, and whether the Lorentz series which I am writing, because Lorentz series is always on a disk, that Lorentz series is whether it is valid in that region in which that isolated singularity is lying or not. That is very important one. Let us see with one more example, that is this clearly. Suppose I want to find out the integral of this function 1 upon z cube minus z to the power 4 on a contour C, where this contour is actually a circle with radius half, center at 0. So this is my circle with radius half and center 0. Now let us see this function 1 upon z cube into 1 minus z. We find it out that at z is equal to 1 and z is equal to 0, both are singular points. Z is equal to 1 and z is equal to 0, both are singular points, and both are actually isolated singularities. Now let us see here, z is equal to 0 means this origin, z is equal to 1 this the point on the real axis. My contour is z is equal to mod z is equal to half, that is the circle with radius half. So certainly the point non-singular point 1, the singular point 1 is outside my region of interest. Inside the contour is only one singular point 0. So I should use a Lorentz series which is valid in the region containing this one. So let us see, if I use this Lorentz series, this Lorentz series is 1 upon z cube into 1 minus z to the power minus 1. We do know again by the Maclaurin's expansion that 1 minus z to the power minus 1, this is 1 plus z square plus z cube and so on. So 1 upon z cube I would get 1 upon z cube plus 1 upon z square plus 1 upon z plus 1 plus z and so on, and this expansion is valid for all z lying between 0 and, that is absolute value of z or the mod of z is lying between 0 and 1. That is the disk which we are having is containing this my region of integral, this contour, and the singularity is inside that contour. So the region which we are taking is that is inside this one. if I use this one from here, if I see what will be my residue, residue is the coefficient of 1 upon z, residue at 0, we want the residue at 0. So, residue at 0 is 1, thus my integral would be 2 pi I. So, the integral of this would be simply 2 pi I. Now, suppose I had made this function in some different manner, let us see. If the Lorentz series I had used this as 1 upon this z to the power 4 I have taken common from here, then what I would get from here minus z to the power 4, if I do take common, I would get 1 minus 1 upon z. So, now if I write the function in this manner, minus 1 upon z to the power 4 into 1 minus 1 upon z to the power minus 1. We do know that expansion of this function is also valid, but for that 1 upon z has to lie between mod 0, between 0 and 1, that says is my mod z has to be greater than 1. So, if I am writing this expansion is 1 plus 1 upon z plus 1 upon z square and so on. So, if I am multiplying it minus 1 upon z to the power 4, I would be getting is minus 1 upon z to the power 4 minus z 1 upon z to the power 5 and so on. What it says is I am not having any term of 1 upon z, that is the coefficient of 1 upon z is 0. This expansion, this series is valid for the disk mod z greater than 1. That says is I would be going outside this one, that is outside this one, while I am actually integrating on z is equal to half, and this series is valid for z greater than 1, that is it is not valid in this region. So, if I am using this series, this would be wrong. So, we have to be very careful, that is what is the reason of integration, that is which is the contour, and the Lorentz series which I am using is that should include that contour. So, here it would be 0, which is really wrong. This is actually at a singularity z is equal to 1, and of course, it is not this C, it will not happen. So, this way we have to be a little bit careful which Lorentz series we are using. Now, since I said is that the Lorentz series we could find out in many methods, and in all these examples I had used simple functions for which this Mach-Lorentz expansion is valid, and we could get the Lorentz series very simply. But are there some methods which says is I could find out the residue without really writing this expansions, this is a lengthy job? That can happen. Let us see. So, we are just finding out the residues at pole. So, if z has this z naught is a singular isolated singular point of f z, then we identify it as a pole if I do have only one term in the principal part b 1 upon z minus z naught. So, if it is a simple pole at z is equal to z naught, my residue would be simply b 1, that the coefficient of 1 upon z minus z naught. Let us see, that is how I am writing it. What it says is that f z would be n is equal to 0 to infinity a n z minus z naught to the power n plus b 1 upon z minus z naught, for the reason 0 is less than mod of z minus z naught is less than r. Now, b 1 is the residue. Let us multiply this whole thing by z minus z naught. What it says is z minus z naught into f z would be b 1 plus summation n is running from 0 to infinity a n z minus z naught to the power n plus 1. Now, if I take the limit as z is approaching to z naught, then we do know is that is if z is approaching to z naught, z minus z naught will approach to 0. That is all these terms will go to 0, and what I would be get left is only b 1, that is the residue. So, what we have got one simple method to find out residue if the function has a simple pole at z naught, that says is residue at z is equal to z naught when z naught is a simple pole of f is limit as z approaches to z naught of z minus z naught into f z. It gives very simple method to calculate the pole, calculate the residue at a simple pole. Now, if it is a simple pole, we can have one more result. Suppose my f is of the form of a rational form, that is f is a ratio of two functions p and q, then what will happen? If fz is pz upon qz and p of z naught is not 0, that is z naught is not a 0 of p, but z naught is a 0 of q. So, that I do, and that 0 is a simple 0. So, that I do have a simple pole at z naught for fz. If this is happening, then what we could say is, because qz is having a 0 at z naught, that says is I could write qz as qz naught plus z minus z naught times q dash z, that is your Taylor's expansion. Since q z naught is 0 of q, so q z naught would be 0. That says is now Taylor's expansion I am writing in different manner, or rather you could say is I am dividing by z minus z naught. I would get q z upon z minus z naught as q dash z naught plus z minus z naught upon factorial 2 times q double dash z naught, and so on. This is the Taylor's expansion of q z at z naught. And since z naught is 0, so q of z naught would be 0. Now, use this same result, that residue at z is equal to z naught of f z is limit z as approaches to z naught of z minus z naught into f z. F z is here p z upon q z. So, if I am writing z minus z naught of p z upon q z, it is simply I could write p z upon q z upon z minus z naught, and q z upon z minus z naught is q dash z naught, and so on. Now, if I take the limit as z approaches to z naught, so now what I am writing is I am writing p z also you could write as a Taylor's expansion, because the z naught is not 0. So, p z naught would not be 0. So, I would get p z naught plus z minus z naught times p dash z naught, and so on. The terms which are not involving z minus z naught, they are p z naught in the numerator and q dash z naught in the denominator. All other terms would involve z minus z naught. So, as z approaches to z naught, all these terms will vanish. What it says is I would get p z naught upon q dash z naught. This is a little more simpler, we do not have to really find out the limit. What we will do, if my function is of the form p z upon q z such that z naught is a 0 of q, but not a 0 of p, that is z naught is a simple pole of f, then residue at z is equal to z naught of f can be given as p z naught upon q dash z naught, that is the derivative of q at z naught. These are the simple formulas. Let us use these simple formulas for the evaluation of our integrals. So, let us see one example. Find the residue at simple poles for the function f z as 9z plus I upon z into z square plus 1. So, we are just going to find out the residue without really finding out the Lorentz series or without really integrating the function. See, the function is 9z plus I upon z into z square plus 1. The function is of the form p z upon q z. If I see this q z, this has a 0 at 0, z is equal to 0, and at z is equal to plus and minus I. All these zeros are simple zeros, since f dash z would be, actually this is z cube plus z. So, f dash z would be 3 z square plus 1. So, for z is equal to 0 or plus minus I, that would not be 0. So, we are getting is that the denominator z into z square plus 1 is having simple zeros at 0 and plus and minus I. What it says is that my this function 9z plus I upon z into z square plus 1 will have simple poles at z is equal to 0 and plus minus I. So, you see that is I have used this relationship between the poles and zeros to find out the poles, and we had find out that this has simple pole at 0 and plus and minus I. So, let us find out the residue at all these isolated singular points, or that is at all these simple poles. We would use the formulas just we had find it out. So, if I find out the residue at z is equal to 0, what we see is that my denominator is z cube plus z. So, rather than having if I do have multiplication of z minus z naught f z, that also is okay, but there I have to find out the limit. If I do use the second method where it is in the rational form, I could use this the derivative of the denominator at that pole point only, and we would get it. So, I am using that method, that is more simpler. So, q z is z cube plus z, this says is q dash z would be 3 z square plus 1. So, p 0 is I and q dash 0 is 1 here. P 0 is would be I and q dash. So, we are getting is that at z is equal to 0, p z is not 0, all these conditions are satisfied. So, my residue similarly at z is equal to I, what I would get, p I, that is 9 I plus I, that is 10 I, and q dash at I would get is 3 I square minus 3 plus 1, that is minus 2. Similarly, if I just go for minus I would get p at minus I as minus 8 I and q dash at minus I is minus 2. So, now what I have find it out, that is this function is of the form p z upon q z. It has simple poles at 0 and plus and minus I. Moreover, at all these pole points, that is 0 and plus I and minus I, the numerator is not 0 at those points. So, we just go with the second one. So, the residue at z is equal to 0 first, p 0 upon q dash 0. Now, p 0 is I, q dash 0 is 1. So, this is I. Residue at z is equal to I, that should be p I at divided by q dash at I. P at I is 10 I, q dash I is minus 2. So, I would get minus 5 I. Similarly, residue at z is equal to minus I. P at minus I is minus 8 I, q dash at minus I is minus 2, I would get it 4 I. So, we have calculated the residue without really expanding this function or finding out any kind of expansions and worrying about what will happen, that is we had just find out at all the singular points what is the residue. Let us use that another method, that limit method. As I said, that is also simple, but here this was more simpler because the function is of this form. So, f z residue at z is equal to 0 of f z would be limit as z approaches to 0 z into f z. If I write z into f z, I would get 9 z plus I upon z square plus 1. Limit as z approaches to 0, there is a much simpler one, as z is 0, I would get here I and here I would get as 1. So, it is I. Similarly, for others you can find it out. Now, if I do have a pole of higher order, higher than 1, it is not a simple pole, is there a simple method in which I could find out the residue? Of course, now we are going to discuss the method for finding out the residue at pole of any order. So, let f z has a pole at z is equal to z naught of order m. Certainly, I am taking m is strictly greater than 1, it is not for the simple pole. If this is happening, then we do know that f z can be represented by this Lorentz series. Summation n is running from 0 to infinity, a n z minus z naught to the power n plus b 1 upon z minus z naught plus b 2 upon z minus z naught square and so on, plus b m upon z minus z naught to the power m. Because it is a pole of order m, so my principal part will take m terms only. Now, let us multiply this whole term by z minus z naught to the power m on both the sides. So, what we do get, z minus z naught to the power m f z is equal to, now I am writing from this side, Bm plus Bm minus 1 times z minus z naught and so on, B1 to the power times z minus z naught to the power m minus 1, plus here again I would have multiplied my z minus z naught to the power m. So, A naught multiplied with z naught, z minus z naught to the power m, plus A1 times z minus z naught to the power m plus 1 and so on. Now, since z naught is a pole of order m, it says is Bm should not be 0 and this expansion is valid for all z minus z naught less than r, mod of z minus z naught is less than r. That says is when I take z is approaching to z naught, all these terms will approach to 0. The only term which would be left is this Bm and that is not 0. But what we want actually? We want the residue. Residue is B1. In this one, if I do see, the residue is coefficient of z minus z naught to the power m minus 1. So, here I cannot go with the simple method, that is limit, taking limit as z approaches to z naught, because I want B1. Now, let us again see this expansion. What is this? I am having it as, you see, let us take it as some d. This is d naught, this is d1, so that dm minus 1, this is dm. So, what I am having is, this is Taylor series expansion of the function z minus z naught to the power m into fz. I am having constant terms, then the terms involving the powers of z minus z naught. That says is my residue for this function f at z is equal to z naught, where z naught is a pole of order m, is actually the coefficient of z minus z naught to the power m minus 1 in the Taylor series expansion of z minus z naught to the power m into fz, that new function gz. So, what it would be? It should be, if we do know that Taylor series expansion of any function gz, the coefficient of z minus z naught to the power m is nothing but the mth derivative of the function gz. So, undivided by factorial m. So, here we want m minus 1th coefficient of z minus z naught to the power m minus 1. So, it should be 1 upon m minus 1 factorial, the derivative m minus 1th derivative of the function z minus z naught to the power m into fz evaluated at z is equal to z naught. So, now what we have got? We have got a formula for the pole of order m, how to find out the residue. So, this is the residue of z is equal to z naught of fz at z is equal to z naught. Let us use this formula for finding out the residue for some functions. You see, this formula would be valid if m is greater than 1, because for m is equal to 1 I would get here 0 and here I would get is d0 upon dz0 and z minus z naught times fz at z is equal to z naught, I would always get it 0. So, this is not, this will not be valid for our simple pole. This formula is valid for the pole of order higher than 1. So, let us see the example. Find the residue at z is equal to 1 for the function 50z upon z plus 4 into z minus 1 square. Let us see this function 50z upon z plus 4 into z minus 1 whole square. We see the function is of the form pz upon qz, and qz has zeros at 4 and at 1. Moreover, you could see is that the 0 at 1 is of order 2, or in other words we do say is that this function has has poles at minus 4 and 1, and the pole at 1 is of order 2. So, this is second order pole at z is equal to 1, and we have to find out the residue at z is equal to 1. So, this here we are having this case where the pole is of order greater than 1. So, I would use the second formula just now we had obtained, which says is that residue at z is equal to 1 of f z should be 1 upon factorial m minus 1, m is 2 now. So, 1 upon factorial 1 dm minus 1, that is d upon dz of z minus 1 square f z evaluated at z is equal to 1. If I multiply this function f z with z minus 1 whole square, I would get 50 z upon z plus 4. So, I have to find out the derivative of 50 z upon z plus 4. You see, that is whenever the functions can will be of the form this z minus z naught to the power m into f z, thus would give actually as a simple function for the differentiation. Now, if I differentiate it once with respect to z, I would get it as 50 times z plus 4 minus 50 z upon z plus 4 whole square evaluated at z is equal to 1. When I put z is equal to 1, here I would get 50 into 5 minus 50, that simply says, or you could say 50 z and 50 z is cancelled out, you are getting is 50 into 4 divided by 5 whole square. So, that is 25 into 4, that is divided by 25, you are getting is 8. So, residue at z is equal to 1 is 8. Now, we had learned here that we can find out the residues using these simple formulations, and we are using these residues for evaluation of integrals. What the evaluation of integrals we had done till now? If f is analytic in and on a simple closed contour, we do know that integral f z dz should be 0. Moreover, we had find it out that if f is analytic in C except at z naught, then the residue method has given that integral along this closed contour C of f z dz is 2 pi I times residue z is equal to z naught of residue of f z, where I was having a single non-singular single singular point or isolated singularity inside the contour C. Now, suppose this contour I do have more than one isolated singularities in a simple closed contour, that is if this kind of thing is, that is I do have this, I have to find out the integration along this contour, and inside that the function is having isolated singularities at the points z naught, z1, z2, z and so on, then what will happen? Can we still find out the residue method or something? Yeah, we can do, but that we will do in the next class. Here we would be. So, today we had learned one residue integration method, which said is that if the function is having isolated singularities, single isolated singularity at a point inside interior to the contour, simple closed contour C, we can find out the integral along that contour, closed contour C, as 2 pi I times residue of the function f at that isolated singular point. This can be extended if I do have more than one singular points, that we will do next time. So, today we had learned one integration method when function is having isolated singularity inside the simple closed contour. That is all for this lecture. Thank you.